A very good morning to everyone. This is Shubhangi Rao and I am working as an assistant professor at MLR Institute of Technology. And today we are going to discuss about the topic boundary conditions for electric field. So what are boundary conditions and why we need to discuss about it while we are discussing about electric field? So we can say when the field exists in a medium which consists of two different medias, then the conditions the field must satisfy are called boundary conditions. So far we had discussed about only one medium, but if we will have two different mediums and the field exists, in that condition the field must satisfy some conditions and these conditions are called boundary conditions. So for electrostatic field we are going to discuss about three different mediums: dielectric interface, conductor dielectric interface and conductor and free space. So one by one we will discuss about all three conditions, all three different arrangements. So first one is dielectric boundary condition. Here if you notice, there is a boundary and at one side of boundary there is one dielectric medium, on other side of boundary there is another dielectric medium, and because we are talking about dielectric medium, there will be permittivity also. So for first medium the permittivity is epsilon 1 and for second medium permittivity is epsilon 2, and as we know the formula for permittivity, epsilon is equals to epsilon naught epsilon r. So for medium 1 epsilon 1 will be equals to epsilon naught epsilon r1, and for medium 2 it will be epsilon naught epsilon r2, where epsilon r1 and epsilon r2 they are the permittivity of the dielectrics or material. So here if you notice, in these two different mediums we have two fields. First one is E1 in first medium, this, and another one is E2, this one. And here what we have done, we have resolved them into two components. One component is tangential component, another component is normal component. Similar thing is done for second field also, normal component and tangential component. So in case of first field, the tangential component is given by E1t and normal component is given by E1n. For second field, normal component is given by E2n and tangential component is given by E2t. Also, here we have considered a small path, closed path A, B, C, D, A, and for this path the height is del h and the width is del w. So this path exists in both the mediums, half-half. So by considering this path, we are going to satisfy some conditions for this particular arrangement, which is called dielectric. So if you notice here, we have already seen in this diagram that we have resolved E1 and E2 into two different components, tangential and normal components. So by this we can clearly understand basically E1 and E2, they are the resultants of their tangential and normal components. So this equation can be written as for E1 is equals to E1t plus E1n, and for E2 it can be written like E2t plus E2n. Now we will apply this equation. Line integration of electric field will be equals to 0 for this closed path. Basically we can obtain this formula from the formula of work done. So for this closed path it will be 0. So we will go one by one. We will go like A to B, then B to C, then C to D, then D to A. So this equation we have to write for all the paths. As integration sign is there, we can write it separately, then we can do algebraic summation. So if we move from A to B, so this is in first medium, this is in second medium. So here the field components are in terms of E1, the field components are in terms of E2 here. So when we are moving from A to B, E can be written as, because it is in horizontal direction, so this tangential component can be taken. This will become, this is E1t, and this dl will become del w. So the first component becomes E1t del w. Now let us move to B to C. So when we are moving to B to C, now this path is there in two different mediums, and this boundary is cutting it into two half-half portions. So when we want to write again for E dot dl, this E, normal component of E will be taken. So for this particular portion, E1 n component will be taken, and for dl, this del h becomes del h by 2. Similarly, for this particular portion, E2n will be taken, and this becomes again del h by 2. Also, we need to check the directions also, because for this field, this is the direction, this is E1n, this is E1t, and here also this is E2n and this is E2t. So when we are moving from B to C, if you notice, when we are writing this component E1n, it is opposite to the direction of E1n. The movement is opposite, so the sign will be negative sign, and dl will become del h by 2. Similarly, when we are moving in this remaining half portion, again it is in opposite direction, so this component can also be written with negative sign, and dl can be written as again del h by 2. Now let us move to this portion C to D. Now again the tangential component in the field 2 is this E to T, but the movement is in opposite direction, so again this E to T will be taken as negative and dl will be taken as del w. Now we move from D to A, so normal components are in upward direction and the movement is also in upward direction, direction is same, so positive signs will be taken, but again because this is divided by the boundary, so half lengths will be taken. So E2n into del h by 2 plus E1n into del h by 2, and the algebraic summation of all these components will be equals to 0. Now we will see how many components are being cancelled. So if you notice, only E1 del w, E1t del w minus E2t del w is common, because E1n del h by 2 is cancelled, E2n del h by 2 is cancelled. So only these two terms are left out, and again it is equals to 0. So ultimately this expression can be written as E1t is equals to E2t. So we can clearly see the tangential components of both the electric fields, they are equal. It can be said that tangential component of E are equal at the boundary. So these tangential components, they undergo no change on the boundary, and we can say it is continuous across the boundary. So tangential component of fields are continuous across the boundary, and as we know, D is equals to epsilon E. So in place of E we can write D by epsilon. So for E1t it can be written as D1t by epsilon 1 is equals to, for E2t it's D2t by epsilon t. So basically this becomes epsilon 2 D1t is equals to epsilon 1 D2t. So here we can clearly see it is not equal, because epsilon 1 is not equals to epsilon 2, and when we are calculating this, these two terms, the numerical value will come different. So we can say that tangential component of flux density undergoes some changes across the boundary. That is why they are called as discontinuous across the boundary, right? So this was about tangential components. Now we can discuss similarly about the normal components, and to understand this we'll have to consider a pillbox kind of structure. Again here we have two different mediums where permittivity is epsilon 1 and epsilon 2, and in place of D now we are considering flux density. Remaining things are similar. This is D1 and again this is resolved into two components, tangential and normal, and obviously d1 is a resultant of d1n and d1t. Similarly, we have d2 and two different components, d2t and d2n are obtained, and to solve this problem, we are considering a pillbox kind of structure and we are going to use Gauss law. We are going to use Gauss law to solve this. So, as per Gauss law, integration of d dot ds is equals to q. So, basically here we have to consider surfaces. Now, if you notice in this pillbox, three surfaces are there. This is first surface, this is second surface, this is top, this is bottom, and this is side. But here we will consider that this height of this pillbox tends to 0. So, when we try to elaborate this, we can write in place of d for this top portion, we can write d1n del s. For this bottom portion, we can write d2n del s. But again, because our d2n, it is in upward direction, but here we are taking opposite direction. So, this term becomes negative. And the third component is for side, but here we are considering del h tends to 0. So, that term will not be taken and ultimately we get d1n minus d2n is equals to rho s. Now, there is one more condition, like if we consider that there are no free charges exist at the boundary. In that condition, this surface charge density rho s can be considered as 0 and this expression becomes d1n minus d2n is equals to 0 and it can be written as d1n is equals to d2n. So, now these two components are same, so it can be said that normal components are of d are equal at the boundary, or they can be called as continuous, right. So, now if you write this component, as we know d is equals to epsilon e. Now, if we write here d1n is equals to d2n is equals to epsilon 1 e1n is equals to epsilon 2 e2n, and then we further rearrange it. So, we can here see that here the normal component of E is going through some changes. So, here we can call it as discontinuous across the boundary, right. So, this was dielectric boundary condition when we have two different medium. There is one more condition for dielectric boundary condition when we are considering refraction. So, now if you notice here again we have two different mediums, but here we are considering a condition refraction, or we will consider law of refraction. Here if you can see, here this is E1, this is D1, again two components E1t, E1n, D1t, D1n. Similarly, we are doing here for the same, this is D2, this is E2, these are normal components and these are tangential components, and two different angles are there, theta 1 and theta 2. Slight difference will be there because that's what it happens in refraction, and these two angles with respect to normal, this is normal, we get these angles slightly different, right. So, let us solve this also. So, here what two conditions we already have, E1 t is equals to E2 t. Now, we will write this in terms of sine and cos. So, if you notice in this diagram, this is E1 t and with normal it is making some angle theta 1. So, obviously this E1 t, if we want to write this in terms of E, it will become E1 sin theta and E2 t will become E2 sin theta 2. Let us give this equation number 1. Similarly, we can write it for D1n and D2n. So, now if we want to write D1n in terms of D1, it will become D1 cos theta 1 and D2 cos theta 2, because now we are writing normal component, it is making angle with normal only. So, this term will be taken as cos term in phase component. Now, this equation is considered as equation number 2. Now, we will divide equation number 1 from equation number 2, and when we put these values, what we will get? This E1, E2 will get cancelled, sine upon cos is tan theta 1, this E2 and epsilon 2 and epsilon 1, they will be cross multiplied, and ultimately we get epsilon 2 tan theta 1 is equals to epsilon 1 tan theta 2. and further rearranging we finally get the formula tan theta 1 upon tan theta 2 is equals to epsilon 1 upon epsilon 2, and in place of epsilon 1 we can write epsilon naught epsilon 1, and in place of epsilon 2 we can write epsilon naught epsilon 2. Again epsilon naught will get cancelled and finally we get tan theta 1 upon tan theta 2 is equals to epsilon r1 upon epsilon r2. So this is called law of refraction, and this is very important for examination point of view. So this was about dielectric boundary condition. Now second arrangement is conductor and dielectric boundary condition. Now in previous case we had taken two different dielectrics. In this case we will take one dielectric from at one side of boundary, and at other side of boundary we will take conductor, right? So suppose this is dielectric side and epsilon is the dielectric constant and it is equals to epsilon naught epsilon r. As we know, inside the conductor electric field is 0. So here there will be no electric field. Only one field will be there, that too in dielectric medium. Again we will resolve it into two components, ET and EN. Again we have to follow the same procedure. We will consider a path ABCD, and again we will elaborate this equation for this path. Now here we don't have E2, we have only E, okay, and its two components T and N. So now let us move to A to B. This can be written as ET del W. Now when we move B to C, so only in this portion it will be taken because second component is not there, so it can be taken as minus En del H by 2. Then here again when we move, this will also become 0, this will become 0. Again we move here, this half portion will become 0. We can directly consider this. So this will be taken as En del H by 2, this term, right? So this all is equals to 0. So finally what we are getting is, which some components will get cancelled, this will be cancelled, this will be cancelled. So we are left with only one component, which is Et del W is equals to 0, which can be written as Et is equals to 0, and E can be written as we know, D is equals to epsilon E. So E can be written as D by epsilon, or directly we can write, if Et is equals to 0, dt will also be is equals to 0, or we can write epsilon naught epsilon r Et is equals to 0. This is the first case. Again for second case, for normal component we will consider a pillbox. Here we will consider flux density in place of electric field intensity, and again we have taken a pillbox. This again it will tends to 0. This will be considered. Okay, so how do we write this equation? Let us see. Gauss law we will apply. Integration of d dot ds is equals to q, and when you elaborate as per the arrangement, as per the diagram, what we will have only this top component, because this is 0 and here nothing is there. So what we get is dn del s is equals to del q, and it can be written as dn is equals to del q by del s, which is nothing but surface charge density. So we are getting dn is equals to rho s, which can be written as epsilon naught epsilon r En. So this was second arrangement. Okay, so some conclusions we can find with that what we discussed already, no electric field exists inside a perfect conductor, and external electric field, if any is there, it is normal to the conductor surface, which is given by dn is equals to rho s. So this was conductor dielectric boundary condition. The third arrangement is conductor free space boundary condition. First case was dielectric, second case was dielectric and conductor, third case is conductor and free space, right? So here again inside the conductor field is 0, in free space field will be there, so E is there, D is there, both the components tangential and normal component of E and D are also considered, and epsilon is equals to epsilon naught epsilon r. So for free space we will see what is the condition. So As we know, for free space, epsilon r will be is equals to 1. And when we put this in equation, already we have got it. dn is equals to, we got epsilon naught epsilon r en is equals to rho s. So this epsilon r will become 1. So we get equation dn is equals to epsilon naught en is equals to rho s, right? And also for tangential component, we have got dt is equals to epsilon naught epsilon r et is equals to 0. Again this epsilon r becomes 1. So we get dt is equals to epsilon naught et is equals to 0 and dn is equals to epsilon naught en is equals to rho s. So this was about conductor free space. So here we discussed 3 different arrangements: dielectric boundary condition, dielectric conductor boundary condition, and free space and conductor boundary condition. And I am hoping it is clear to everyone. In case of any doubt, please write to us. Thank you very much.